And then we've got Arthur Cohen and Pierre Emmanuel, respectively, have been working on Gccrs for 4 years and 2 years, and I will let them get on with it.
Hi everyone. So yeah, this talk is titled Inching Closer to the Rust Standard Library with Gccrs. It's going to mention roughly some of the interesting stuff we've had to deal with in the last year of development with Gccrs. The first thing I'm going to talk about is like a little bit of an introduction for us. This is supposed to be a Venn diagram, but as you'll see, I'm better at compilers than I am at graphics design. So both Pierre Emmanuel and I work at Gccrs MSAS. We do compilers. We're both co-lead on the Gccrs project, and we're both full-time compiler engineer on Gccrs. We're both French, so please excuse the faint cheese smell permeating through the room. Pierre Emmanuel is a systems programming nerd. He's also a university lecturer, which is quite cool. Me, on the other hand, I just love programming language, and I have a cute dog. So, yep.
Okay, so a bit of context. So what is Gccrs? Gccrs is an alternative compiler for Rust. It is a front-end in GCC. It started when Rust was in version 0.8 back in 2013. Yeah. And basically, project stopped for a few years because Rust was evolving too quickly, and project started again in 2019. We target Rust 1.49, and why is that? Because Rust 1.49 has no const generic, and we didn't want to implement them because they were deemed too complex at the time. And guess what? We want to be able to compile a core library and as well as a standard library, and both of those libraries are using some nightly features, and among those features are the const generics, so we're doomed. You can probably already test your Gccrs within your own GCC on your laptop, because Gccrs is included in the past GCC release, GCC 15.1, unless your distro maintainer hasn't enabled the Rust language. So yeah, get back to it.
So what are the goals of Gccrs? Sort of the main reason for why the project was started is that compilers are fun. Only people that love compilers would tell you compilers are fun, but still. One of our main goals is to not step on anyone's toes. So over the years, we've had, lots of people thinking that Gccrs could split the ecosystem in half or make it harder for crate maintainers to keep up with two different compilers with two different feature sets, which is something that you find in C and C++. So it's been very important for us to not do that and to actually learn from past mistakes. So we're taking, some steps and some measures to ensure that, people know Gccrs is not ready. If your crate doesn't compile with Gccrs, it's probably a Gccrs bug, not an issue with your crate. This is why we have this very, very long and annoying command line flag that won't let you compile anything unless you specify it. This is the source of a lot of issues with the rest of the GCC community that does not like this flag at all. One of the goals is also to help bring Rust to more targets and more systems. Back when the project was started, GCC supported a couple more or a lot more targets than LLVM, and it was a good way to get Rust on those platforms if you want to use Rust on your Soviet era satellite or something like that. But now, of course, we got Rust C Code Gen GCC, so that's a bit of a moot point because they do that better than us. Still, it's still going to be useful for compiling all of Linux with just one compiler. So, now that there's Rust in the kernel, we can also do static analysis on unsafe Rust code. Basically, for the kernel, if you're a kernel developer and you're writing up an abstraction over kernel components, like C file descriptors or variable arguments list or something like that, GCC is quite good at catching garbage C code because, well, it's been 30 years we've been writing garbage C code. So when you're writing, unsafe Rust dealing with annoying garbage C stuff, GCCRS can help sort of, do safety analysis on that. We also plan on reusing components from Rust C. We'll talk a little bit about that in a future slide. And we also want to help review the specification effort, which is why Pierre Emmanuel has joined the spec team a few months ago, and sort of bring a different educated viewpoint as users and consumers of the specification and the Rust reference. We wrote a blog post on the official Rust blog about our goals, our ethos, and the stuff we care about. So please go ahead and read it. And yeah.
Just to clarify, I did not join the T-Spec team. I only joined the spec
Yeah, the
calls.
spec calls, sorry.
So why do we want to compile STD? So most of the crates on crate.io require the STD, the standard library. You wouldn't be able to do most things you do in Rust without it. I believe there's probably don't quote me on that, but probably 1,000 crates on crate.io that supports no STD, so that's really, really low. The standard library is really multiple libraries because it has direct dependencies to core, the alloc crate, and libandwind and such. So yeah, and Gccrs is developed for Rust for Linux, and Rust for Linux is using the core crate as well as the alloc crate, so we need to be able to compile those two crates in order to compile the Linux kernel. Embedded Rust doesn't use STD, but Embedded Rust still use core because people don't want to redefine every time they write a new project or lang items every bit of annoying Rust, which are let's say option structure. You don't want to define the options every time you write a new product. Yeah.
So yeah, what's in core? As Pierre Emmanuel said, core is sort of a very intrinsic crate to the Rust programming language. A lot of the stuff that you use in Rust are declared within the core crate, but actually defined in the compiler, so stuff like lang item, intrinsics, and whatnot. So core is actually a super mega complex piece of Rust code. It's a great place for experimenting with a lot of nightly features, which makes me very, very sad because that means, not only do we have to support Rust 1.49, we have to support everything that's nightly in Rust 1.49. We can name a few. Some of these have been stabilized, since then, because 1.49 is 3 years old at this point. So things like specialization, const generics, macros 2.0, negative trait implementations, or the raw reference keyword.
In the past, and for a long time in Gccrs, we've been working with snippets. So we basically took some fancy snippets of Rust code that we did like, and we tried to run a compiler in it. And usually the compiler did throw a big error message and gave us some ice or whatever. And basically it didn't work, and we fixed those bugs, we fixed those things, but it was really not homogeneous. So we've changed our methodology in order to focus on core, because we wanted to be able to compile the basic blocks required for Rust program before being able to compile even harder code. So what we changed is we tried to compile core. Obviously it did not compile. We had a lot of error, a lot of stuff, a lot of bugs, and we tried suppressing those bugs and those errors by changing its core library, and making a list of what went wrong. And we were shrinking the core library bit by bit until it compiled. And we discovered a lot of things that did not work. So for example, a lot of lang items were missing. The old name resolution could not keep up. More on that later. And we were missing a few intrinsic. So let's take a look at these short snippets. Everyone should be able to understand it. I mean, it's a 3-line it's a loop. It obviously has a 9 iteration, and it prints a message as well as the iteration number. So if you take a look at the QR code, you may be able to access the link we'll present now. Yes? No. Okay, so this is the assembly generated by Rust-C for those 3 lines of code. Because under the for loops are desugared, and there are a lot of traits, like for example iterators, into iterators, and a lot of things that are generated that will be optimized out later, but the raw output of Rust-C is really that assembly, 173 lines of assembly for only 3 lines of code. And most of us would have expected, like, let's say, 20 lines of assembly, a bit more, but yeah, under a simple for loop, there's a lot more. As I said, you need range, iterator, you need 2 desugar for loops, you need also the external library. Behind this print and macro, there's the format arg macro as well as the print function. And if you need the external library, you need the alloc crate and you need core crate, so all those stuff.
So one of the things that we finally did this year was actually that for loop desugaring. And I can tell you that when you tell your employer that after 5 years of compiler work you can finally handle for loops, you get strange looks. But we'll take a little bit of a look as to how for loops are desugared in Rust. This is roughly what it looks like. So our simple for loop got, a lot more lines now. Basically, you can see all the components from the previous for loop. You got the range, you got the iterator variable, and you got the body of the for loop. This is what Rust-C does internally. Desugar, like change your for loop into something like this. But actually, it's a little bit more complicated than that, because Rust-C desugars to the following path. To actually call, methods and traits within core, and not just a trait that has the same name defined right above your for loop or stuff like that. And if you know a little bit about Rust, you'll be able to tell that resolving a path that starts with : core means you want to resolve it in the core module or the core library, except we still can't compile core. So in order to have for loops defined in core, we need to be able to compile core that uses for loops that resolve to path used within core. And suddenly you get into a chicken and egg problem, and we can't have any unit tests. And that's really annoying because we don't have all of core, but we still want to test our for loop. So one of the things we had to do that Rust-C doesn't need to do is we had to implement lang item path within our AST. So in Rust-C, these lang item paths that refer to very important and intrinsic methods or traits within the Rust language, they're only used in the HIR. But we had to sort of redo a bunch of stuff in our AST to be able to desugar to this and actually be able to call into the proper next or the proper intuiter method that was marked with the lang item. Another thing we can look at is the iterator next method. One thing that's used in core for this specific method is specialization. So I'm going to dig into a little bit of why specialization is used and what it is. The reason that the core library uses specialization is for performance reason. So in some cases, iterating on stuff where, for example, you know the length of the stuff you're iterating on, well, you can do unsafe pointer magic and it becomes faster. So what is specialization? It's one of the things I personally hate about Rust, no offense. It's rarely used in core and only for optimization purposes. So basically, both the generic and the specialized method will have the exact same behavior in core. One will just be more performant and more sort of precise. And so that means we must support a subset of it, even though, you know, specialization is still unstable. It was very unstable in 1.49. It's just not very present in, I want to say, everyday Rust code, but still. So a simple example is the following. You got a trait waffle that turns anything into a waffle. And you can implement a generic waffle for every type that implements clone and a generic waffle for every type that implements copy. As you know, if your type is copy, well, your type is also clone. So you'll get an ambiguous, you know, method resolution error if you try using waffle on something that implements copy, because Rust doesn't want to decide whether to use the clone version or the copy version. So you can solve that with specialization. You can mark one method as more generic, as specializable, as less precise than the other. In that case, we'll have, for example, the clone method be slower and more generic, and the waffle method on copy be extra precise. And then your code will work. If your type implements copy, it will select the bottom implementation. If it only implements clone, it will select the more generic implementation from the top. And you can get even more precise. For example, you can decide that every time you pass an ampersand string, you want to return waffle anyways. And so now you have, you know, two methods, two implementations that are specializable, and one very precise method. And this is something we've dealt with this year, because in that case, it's kind of easy to, you know, figure out which one is the more precise method. It's just the one that doesn't have a default keyword. That's what used in core. This is what I thought we had to implement for handling, you know, the standard library. I was quite happy, figured it out all by myself. Turns out alloc uses that pattern as well. So now we have to do the full specialization, preciseness, graph analysis thingamajig, where we have to decide which one of the two default methods is more precise. And that's going to be sort of our life for the next few months. And yeah, I'm not looking forward to it. And yeah.
We've got our for loops desugared, and we still miss the println macro from standard library. So this is time to talk about the integrating Rust C component. If you take a look at the println macro, it has a format string inside, and for GCC we wanted to reuse some components. For example, we wanted to reuse Polonius for the borrow checking, and the first step in that direction was reusing the format arg parser trait in order to pass those println macro and every format string in Rust. We did choose this because it was quite small and we wanted something easy to integrate into Gccrs before tackling something more difficult like Polonius or whatever. And we plan on using and integrating more Rust components. For example, the next trait solver, or even some work from the Safe Transmit project. And obviously, we already integrated the Polonius borrow checker, and we plan on integrating the next borrow checker. But this means we will need to help an effort to creatify it and kind of get it out of the Rust C compiler itself. Not that we can't reuse everything, because obviously we have very different structures from Rust C. So for example, our AST has a very different form than Rust C, and each has a different structure with different statements and expressions, and we cannot just bind it one-to-one to REST structure, so we can't reuse everything. But we do want to reuse a lot of things to reduce the gap on things that are important and really complex to manage. Yeah. Here are a few honorable mentions. So, I think we tackled recently in order to compile core. So, the LLVM ASM macro, but obviously we wrote LLVM, so we cannot cheat a little because obviously this was a nightly feature, and nightly feature in 1.49, and it was used only one time in core for the black box int before it was intrinsic. So we implemented a subset of the LLVM ASM node in order to be able to parse and compile black box correctly. We'll talk about derive partial all later, and yeah, the name resolution. We had to completely rewrite our name resolution.
So yeah, we also took care of built-in derive macros this year, so things like partial OR. I think the slide is going to speak for itself for why it was annoying to deal with. A very simple, tuple expands into a recursive match statement where you have to keep comparing fields together. I'll let you imagine what it looks like when you got like 10 fields or when it's a tuple inside of an enum, and yeah.
Yeah, so let's tackle name resolution 2.0. So basically, name resolution in Rust is a really complex piece of code because it runs in 3 different passes: top level, early pass, and late pass. And also, it uses some fixed point macro expansion because you can expand things that are not yet existing, and you need to be able to resolve those. We'll bring you an example in a few moments. Also, globe imports are also complicated because basically you need to bring in scope. For example, let's say you have a wildcard globe import. You need to bring in scope all components from the model you're importing, but you need to be able to shadow those components quietly if some of the component has the same name in your scope. Initially, Arthur said we could rewrite it in 3 weeks, and it was September 2023. We are now 2 years later, and it's still not done.
It's almost done.
We still have a few things to fix, but yeah, almost done. Name resolution is really another beast. It's a Rust compiler is really not your average single pass C compiler. All the burden that has been put on the user in C, for example, or C++, has been put on the compiler. And yeah, we'll take a look at a brief example just to showcase one case of the name resolution. Keep in mind that it's really not the most complex example in the world. We will deal with something really simple, but yeah. So let's take a look at this code. So here, yeah, we've got a macro, and this macro expands to another macro definition, and it is called over here, and the inside macro is called over here. So what's going on? We are coming from previous passes from our compiler, and we're going through TFD stripping, and we are now on our top level name resolution. This means we will collect all crate definitions. So here the compiler will collect the outer macro definition as well as the main definition. Then the compiler will proceed to the early name resolution. So in this pass, the compiler tries to match macro invocation with macro definition. So here it tries to match outer, and it match outer with this definition. But this macro definition hasn't been found yet because it hasn't been expanded. So this macro invocation cannot be can be found. So we need to collect the error, and we do not emit it directly. We need to simply collect it and progress to the next pass. Next pass is expansion. So here the compiler will expand all macros available, and it expands the outer macro at its invocation site, and here this gives us this macro definition. Here there's two paths: either continue, or we could go back up to the CFG stripping path. So the compiler will take a look at the AST. Has the AST changed or not? And if the AST has changed, it should go back to CFG stripping path. If the AST has not changed, it means that no macro has been expanded, and it could basically continue because every item has been found at least one time. So we're going back up the loop. So we skip CFG stripping because not important. For this example, top level again. This time the compiler can see the inner macro definition. Main can be found again. We go back to early definition. Inner can be found and matched to the macro definition, so it can be expanded. You basically got your main function. And it is not done yet because, I mean, println is a macro, so the compiler would have to do a few more loops in order to expand really everything.
So yeah, what are the next steps for Gccrs? Basically, we are quite close to being able to compile core. I think once we'll be able to compile core, alloc will come sort of naturally, and STD should not be too far behind or too complicated once we, can handle core. That's going to let Gccrs be useful for a lot of projects. It's going to be useful for embedded Rust, as we said in the beginning, and our next target is for Gccrs to be useful for Rust for Linux. So one thing you may know about Rust for Linux is they use a very recent version of Rust, certainly not a 3-year-old one. So we'll have to first sort of catch up to more recent Rust or stable Rust, which will mean that we'll have the first compiler for Rust 1.49 that will be able to handle some features for Rust 186. You may think that, in the last 3 years of Rust development, there's been a lot of changes on the language. But if you actually look at all of the release blog posts, you'll see that most of the changes are features being stabilized or APIs being added, or new types, new functions, stuff like that, stuff that we should be able to handle in the first place. So the language itself does not have that many changes. We can name a few. For example, in the last release, we have trade upcasting. In 1.84, we have the use syntax. We also have, things like return position impl traits in traits. Sort of the saving grace is that a lot of that stuff is type system stuff, and I don't do type system stuff, so it's going to be someone else's problem. And there's also, some things that have been stabilized since 1.49, but that we already need to handle to, be able to compile core in the first place. So things like const generics are used in core 1.49, const blocks are used in core 1.49. The offset of macro is used or already exists in 1.49. So sort of the point of this slide is that even though it feels like we're, very far with a compiler that targets a 3-year-old Rust version, I think it's actually going to be useful quicker rather than later, something like that. But yeah, in a little bit of time. And we do plan on being able to compile core very soon. We plan on starting to compile Rust for Linux at the end of this year, definitely for the next GCC release in a year. And yeah, we hope that it's going to be available and that you come check it out. There's links to everything we have, our repo, our Zolip, our IRC, and Yeah, thank you.
So are there any questions?
Why did you choose to compile core instead of making your own standard library?
So we, as we said in the beginning, we want the least sort of ecosystem breakage between Rust-C and Gccrs, and we do have sort of a target to be as close to Rust-C's behavior as possible. So that means, you know, bugs and all, every sort of thing that Rust-C does. We
Does that
thought
mean you're targeting nightly features as well, that you want to match nightly features bug for bug, not just stable features?
so nightly features that we need. So for example, for compiling core or Rust for Linux. But once, you know, it comes to, you know, like stable Rust, the goal is to be a stable 1.49 compiler without necessarily all of the nightly features, if that makes sense.
Right, but if you had your own standard library, then you only need to support the nightly features that Rust for Linux uses, not all the nightly
Yes.
features that core uses.
Yes, but dream big, I guess. It's yeah, we just want to be able to use the same standard library, same everything, to have the least sort of divide between the two compilers, if that makes sense. As I said, ever since I joined the project, it's been really important for me to, you know, make sure we don't hurt any project, we don't hurt anything, we don't cause unnecessary divide, unnecessary attention, we don't bring back, you know, some of the stuff from C and C++, and just, it felt like reusing the exact same standard library would be a good idea for that. But yeah, it does make our life harder, so yeah.
Thank you.
Thanks.
Hi, great talk, thanks.
Thank
Did you
you.
ever think about not implementing specialization and just using the default impulse because they would still be correct in theory, even if they're slower?
Yes, so that's completely something I wanted to do. Then I realized that, you know, choosing between the default impl and the specialized one was quite easy in the easy path. And, you know, in, as I said, I think in stable alloc, or maybe it's alloc from 1.49, we have to handle that pattern of the more precise impl still being specializable, still being, you know, default. So turns out we have to handle specialization either way. In the end, it doesn't make a big difference if it turns out like that we choose the wrong implementation, because as you said, like both implementations are supposed to do the exact same thing. It will have an impact on like the runtime performance of the compiled binary. But just for compiling core and for compiling the standard library, it shouldn't make a big difference. So yeah.
Cool, thanks.
Thank you.
Another question. Oh, I see one.
Si tu veux répondre, n'hésite pas. Si tu veux répondre.
Thanks for the talk. If I understood correctly, the intention is to support all of 149, but with some features from later. For some of the larger features, like return position infiltrate in trades, that have been a significant effort in Rust-C to implement, have you been architecting your compiler in such a way that with an eye towards supporting that in the future, or is that something that you are only now looking at how to implement?
So that's an interesting question. For some features, definitely, we did that. For some features like return position infiltrate in trait, definitely not. It's going to be a massive, probably refactor, or there's going to be, you know, massive churn to the code. I guess we'll see. We're not in a position, you know, where we have to go through a lot of process to make massive changes to the code base. Sorry, it's still very experimental. We have a team of, you know, like 15 people. We don't have that many users. Like our first users are going to be, you know, for example, the Rust for Linux team, and I think they're not afraid of using a compiler that breaks or having to compile GCC by hand every few weeks or stuff like that. So even if it is a massive churn, I think it's not going to be that bad in the end to implement those features. And also, I feel like for a lot of features that took a long time to develop for Rust took a long time to develop, because obviously the Rust people take pride in making them good, making them usable, making them sort of perfect and nice to use, and they think about everything. And we don't have to do that. We can just use your work and use the final good result and implement that. So it's also easier for us. And yeah.
Are there additional things that we could be doing from the Rusty side to help you guys?
I think sort of the relation that Pierre Emmanuel and I and Philip and everyone from the team has been trying to foster from the past few years is how can Gccrs help Rust C instead? Because no one asks us to do that, and like, who are these guys bothering Rust C with their shitty fun project? So it's more with, again, like, we don't want to step on anyone's toes or make you guys do any more work or stuff like that. Definitely, like, everyone has been super helpful whenever I come into the Zulip asking for dumb questions about name resolution, or I've had help from so many people in the Rust community working on Gccrs. So I don't think so, but I'll let you know.